kick things off for this part of the agenda with introducing Dr. Laura Christensen, and we've tried a few times to get Laura over to the forum, and so fortunately third time was the charm, and we've got Laura with us today, and she's one of the leading researchers on denitrifying bioreactors, and just got a new CIG that is going to be looking at some innovative bioreactor and saturated buffer design. So looking forward to working with her on that, and we'll turn it over to you, Laura, to talk a little bit about bioreactors.
Great. Thank you, Chris. Can you all hear me?
Sounds good.
Okay, great. And I think you can see my full screen. So I wasn't nervous to present at the Iowa, Minnesota, South Dakota Drainage Forum until I saw the numbers continue to kind of skyrocket this morning. So thank you all for attending the forum, and thank you for coming back after the break to listen to my talk and others following me. Straight off the bat, I wanted to acknowledge our funders. I'll be showing you parts and pieces from a variety of different studies today. So funders and partners here, and I would also be remiss in not acknowledging the broader team who's done this work, especially acknowledging the students who are doing the heavy lifting for these studies here, starting with Mary Foltz, who's in the orange shirt on the left of the screen, Miss Naranga Wickrama-Rothney, who's in the picture, the second from left, and then Gabe Johnson, who I think I saw attending. Gabe Johnson is in the picture in the middle. So thank you to the students. And as you would have guessed from the title of my talk, we'll be talking about the wood chips that go into wood chip bioreactors. I'm assuming that most of you on the call today, on the line today, know what a bioreactor is. So I'm not going to explain what a bioreactor is, but over the past 10 years or so that I've been doing this work, the most common question that I continue to get is, does the type of wood chip matter? And so we're going to be talking about that a little bit for the next 20 minutes or so. Of course, one of the best places to start when we're talking about bioreactors, and especially the wood chips that we use in the bioreactors, is the conservation practice standard from our very own Natural Resources Conservation Service. Now, those of you who are heavily in this field will realize that there is a new conservation practice standard for bioreactors that was released just a couple months ago at the federal level. This update to the practice standard includes some important changes, kind of streamlining for the performance and capacity design criteria, but we're not talking about that today. We're talking about the wood chips in the bioreactors themselves. So you don't need to read all of this. We're going to walk through the parts that I want us to talk about. But this, of course, is the wood chip specifications in the conservation practice standard. And this is going to be kind of our home base. This conservation practice standard sets the context for the wood chips that we use in our bioreactors. And so I want to make the point from the top that I'm not trying to poke holes in the NRCS conservation practice standard, or I'm not trying to harangue the NRCS or the idea of practice standards. In fact, many of you will agree that the NRCS is one of our most important partners for getting conservation on the ground. And we're using the conservation practice standard as an example today, because again, this is the context for how we do bioreactors here in the United States. So let's go ahead and walk through some of the parts of this, the media specifications here, starting with the criteria of selecting wood chips that have a low tannin content. Now, this low tannin content criteria comes from basically a restriction on the use of oak wood chips in bioreactors. Oak is a very high tannin wood, and actually the word tannin comes from an old German word tanna, T-A-N-N-A, which means oak. So oak and tannins are kind of intrinsically linked, even in the meanings of the words. What I'm showing on the left of the screen is a documentation from a farmer partner that we've just started working with. They have a bioreactor, and our farmer had to supply this information from the sawmill that they got their wood chips from. They supplied this document to the NRCS to guarantee that the chips that they were using in their bioreactor contain less than 50% of oak wood chips. And I thought that this actual documentation was interesting to see that this actually had to be provided for the NRCS to meet the practice standard. Now, this got us thinking a lot about the use of oak in bioreactors. And so I'm going to talk about one experiment where we studied three kinds of woods, which are listed there on the left, that allowed us to look at leachate from oak, which is what I'm talking about. It also, in thinking about oak as a common wood species across the Midwest, certainly in Illinois, we also started to think about another common wood species, ash trees, which have been greatly impacted by the emerald ash borer. So we'll talk about this one experiment, these two parts to this one experiment. Let's start with the first part. So I've highlighted oak on the left of the screen because in this first part of the experiment, we're really interested in how bad, quote unquote, are oak wood chips in a wood chip bioreactor. And so in this first part of the experiment, the oak is really the treatment that we were interested in. And those other two wood chips listed there, we consider the control for comparison with the oak as a treatment. The methods in brief for this experiment, all of the three kinds of woods that I have listed were chipped on the same wood chipper. They're all sieved to the same particle size. All of the little bioreactor cells were packed with one of those three kinds of woods listed on the left, and all of those bioreactor cells received nitrate-dosed pond water. All of the bioreactor cells were operated at the same hydraulic retention time of about 8 hours, and we're looking at the first 84 days in this first part of the experiment, where we would have the most kind of leachate coming out of the wood chips. What we found, not surprisingly, was that the oak leachate, especially in the first days up to about 2 weeks, the oak leachate was definitely darker than the leachate coming out of the other wood types. Now, this wasn't a very quantitative way to look at it. And so to actually put some numbers to these colors that you're seeing, we use the method of analyzing the samples for true color. True color is a standard method for waters and wastewaters. It's not something that we often do for drainage water, but true color is measured in platinum cobalt units. And the interesting thing with true color is that it's not turbidity. It really is a measure of color, how colored the water is, because as you saw from the pictures that I just showed, that wood leachate is often colored, but it's clear. So again, this is not a measure of turbidity. It really is how darkly colored the sample is. As you see from the graph, the oak leachate is definitely more colored than the other two woods that we studied in this experiment. And note that the Y scale is actually a log scale. So the oak was much, much darker, which you also saw from the picture. Now, what we were really interested in with this study was the tannic acid coming from the wood chips, because again, it's the high tannin nature of the oak that we wanted to study. So tannins and lignins in water are evaluated using a method that measures tannic acid. So that's what I'm showing on the y-axis for this top figure. What we found was that after a period of time, really about 50 days at the outside, the oak really became no different from the oak leachate, or the water coming out of the oak wood chips became no different, not statistically different from the water coming out of those other two kinds of wood chips. So that while oak leachate is very distinct initially, you do get to a period of time, you do get to a period after sufficient flushing where the oak leachate isn't any different, isn't any worse, quote unquote, than the other two wood chips that we tested. Because things like tannic acid and true color are not normally things that we talk about for drainage water, we did want to put our leaching experiment in context of things that we are more familiar with, like stream water. And so we analyzed about 24 samples from local streams for these same parameters. What we found was that actually the streams that we the stream samples that we analyzed had higher tannic acid concentrations in the stream water than the bioreactor cells at the end of our flushing experiment. So this wasn't the initial bioreactor cell outflow. This was at the end of the flushing experiment. The streams had higher tannic acid concentrations. We found the same thing for true color, which was also a little surprising. The stream samples happened to be slightly more colored than the wood chip leachate at the end of the experiment. We found the opposite trend for chemical oxygen demand, which is basically a measure of the carbon coming out of the wood chips. And this really isn't surprising because this is how bioreactors work. They release a little bit of carbon into the water, and that's what fuels the denitrification. To really throw a little bit more at this question of tannic acid and wood chips, we also wanted to analyze outflow samples from some of our full-size bioreactors that we monitor across the state. I'm showing 5 of our bioreactors there in the top figure. And what you'll notice is that the tannic acid concentrations coming out of our bioreactors over time generally show a trend of decline, which roughly mimics what we were seeing from the small-scale leaching tests. The peak that you see with those red squares from the Dudley Smith Farm bioreactor, that peak actually coincided with a relatively dry period at the bioreactor, where we had a couple small flow events you can see from the flow data at the bottom of the slide. So we did have some water moving through the bioreactor, but curiously, not all of that tannic acid coming out of the bioreactor was just from the wood chips, because we did also see tannic acid concentrations going into that bioreactor elevated during that dry period. So that was something that I didn't expect to see, but tannic acid possibly could be coming from the soil too. So coming back to this slide, to bring us back around, oak could be, I will say, could be an important source of wood chips for wood chip bioreactors, because it's possible to flush that distinct leachate down to a point where the oak wood chips essentially are no worse, quote unquote, than other kinds of wood chips. There's some trade-off here. There could be a risk versus benefit type situation when we talk about oak wood chips, because we also need to look at how costly it might be to find wood chips that we can guarantee don't have any oak wood chips in them. So I think there could be some trade-offs that we want to talk about. However, the oak story is not quite done. Stay posted for another couple minutes because we're going to come back to oak in a minute. But I do want to move on to the second part of this experiment, where we looked at emerald ash borer killed ash tree wood chips. And the real question was, is there anything inherently different about wood chips from an emerald ash borer killed ash tree that would preclude their use in a bioreactor? Or in other words, is there anything that the emerald ash borer beetle does to the wood that would preclude that wood from being used in a bioreactor? So again, the same methods that I talked about before, but in this part of the experiment, our treatment is the emerald ash borer killed ash wood chips, and the other 2 woods are our controls. And then we're really looking at the end of the experiment rather than the beginning of the experiment. So in this case, we're looking at the last about 100 days of steady state operation. And we found that there was actually no significant difference in nitrate removal provided by those EAB killed or those emerald ash borer killed ash tree wood chips versus our mixed hardwood blend. So seemingly there is nothing physiologically different that the emerald ash borer does to those that ash wood that would decrease nitrate removal to where you wouldn't want to use these ash wood chips in a bioreactor. So that was a good thing to find out. However, the real shocker, I hope you are all sitting down, because the real shocker for this part of the experiment was that the oak wood provided significantly more nitrate removal. And we weren't really expecting to find this, but again, all of these wood chips were sieved to the same particle size. They were all operating with the same water at the same hydraulic retention time. So we wanted to dig in to the oak question again, a little bit more to figure out what was going on with the oak. Why was it performing a little bit better? The way we dug into that question was by performing what are called denitrification enzyme assays, also known as DEAs. Denitrification enzyme assays are a test that's a little more commonly done with soil rather than wood chips. The idea is that with a DEA, you provide an exactly ideal environment for denitrification to occur with a given substrate, like a certain soil, or in this case, our 3 different kinds of wood chips. What the DEA tells you is the maximum potential denitrification rate that that substrate can support if the conditions are exactly ideal for denitrification. And what we found was that oak, something inherent about oak just happens to provide more potential for denitrification to happen. So there is something very different about oak. And in this case, we found that oak does provide more nitrate removal and has a higher potential to support denitrification. So coming back to the emerald ash borer question, though, we did find there's nothing physiologically different about trees, ash trees that have been killed or impacted by the emerald ash borer, where you wouldn't want to use them in a bioreactor. But we do need to be respectful and cognizant that there are quarantine boundaries. So we don't want to be transporting EAB killed ash chips across a quarantine boundary because we don't want to spread this terrible forestry pest. When we looked at the federal quarantine boundary, what we found was that there is a significant amount of tile drain land within the federal EAB quarantine boundary, which basically says there's a significant amount of places that need bioreactors that fall within the federal quarantine boundary where we wouldn't have to transport ash chips across that quarantine boundary. Now, I'm not showing state level boundaries, state level quarantine boundaries, so that's also something you would consider. Also, in recognition that this is the Iowa, Minnesota, South Dakota Drainage Forum, you'll see from the map there's significant parts that some of you live in that fall outside this federal quarantine boundary. So what I'm saying is very contextualized for us in Illinois. We're within the federal quarantine boundary, but some of you might not be. So back to our conservation practice standard, the next thing that I'll talk about is actually the physical size of the wood chips. And we see the NRCS wants us to use wood chips that are relatively coarse, and they even put a number on it, 1 to 2 inches in effective diameter. And that term effective diameter, that's going to come up again, so keep that in mind. So the way we tackled this, or the way we started to put understanding to this, was basically perform particle size analysis on a variety of wood chips across the Midwest. Every wood chip that we could get our hands on, we've done particle size analysis on. Looking at the legend, the top half approximately of the legend represent wood chips that have gone into bioreactors that we're monitoring here in Illinois. The bottom half of the legend refers to those bulk chips or wood chips that could be bought or purchased somewhere that you would possibly use in a bioreactor. The bottom of the legend, the D50, that's the effective diameter when you do a particle size analysis. D50 is the particle size that 50% of your wood chips are larger than and 50% of your wood chips are smaller than. It's essentially the 50th percentile or the median diameter. This is also called effective diameter. What I want to highlight here is that none of the wood chips that we've sourced fall within the 1 to 2 inch effective diameter. So we might be using that term a little differently. What do some of these wood chips look like? They actually look fairly big, but again, they're actually measuring smaller than what they would look like. And I see I'm running a little close to time, so I want to keep us on track. So I'm going to skip through. Again, just to reiterate, this is the same data shown in a different way. The D50 that we're finding for nearly all of our wood chips is very close to 1/2 inch. 13 millimeters is roughly 1/2 inch. So we're not getting close to that 1 to 2 inches that's in the conservation practice standard. However, I will say, I'll end with, wood chips are not spherical, and a particle size analysis is best with media that are spherical, like soils. And so in addition to doing particle size analyses, we're also measuring wood chips by hand to see how the particle size analysis compares with our hand measurements. What we see from wood chips that tend to be relatively uniform, like these I'm showing here, the particle size analysis actually matches the hand measurements relatively well. Like I said, these wood chips are relatively uniform. They also tend to be squarish in shape. That's compared to wood chips like this, which are very shredded and long and skinny in shape. These wood chips actually don't match the particle size analysis that we've done very well. The manual measurements don't match the particle size analysis. So I will just wrap up by saying, in terms of oak, I feel like there's a trade-off. We certainly don't want to create a water quality problem with our wood chips in our wood chip bioreactors, but I also don't want to see any potentially unnecessary barriers to doing bioreactors by making it really hard to find wood chips that are going to be suitable. So I think there's some trade-offs there. There was nothing inherently weird about emerald ash borer killed wood chips that would preclude their use in a bioreactor, but we do need to be cognizant that there are boundaries that we don't want to be transporting these this pest or these wood chips over. And then lastly, we're still trying to figure this out, but the wood chips are measuring quite a bit smaller than what the conservation practice standard calls for. And so, like I say at the top, this is good job security for us. There's still a lot to learn about the wood chips we use in bioreactors. And with that, thank you. Back to you in the studio, Chris.
All right, great. Thanks, Laura. And so we're running close to time, and so we did get a few questions in the chat, but we'll have some time right before lunch to do a little Q&A. So we'll save those questions till then. So I'll go ahead and introduce Asan Ghane. Asan's at Michigan State University, and we'd planned to have Asan on the agenda last year, but I think it was, if I remember right, as a combination of mechanical and weather issues that prevented that. So we were glad to get him to be able to join us this year. And so Asan's another one that just got a recent CIG and is doing a lot of work on tool development with some drainage tools. And so looking forward to working on some work on saturated buffer decision support tools with Sonic coming up. So I'll turn it over to Asan to talk a little bit about design drainage rates.
Thank you a lot, Chris. Can you give me access to share screen? This is my second time presenting at the Drainage Research Forum. The first time was when I was in Minnesota. I was a postdoc, and I remember Gary Sands invited me and I gave a talk about wood chip bioreactor, and I really enjoyed this group. It's we have industry, practical, engineers. So is this ready? Still not ready. So yeah, so back then I was doing wood chip bioreactors, and when I moved to Minnesota, I got it. So when I moved to Minnesota, I started working on controlled drainage, saturated buffers, and basically drainage. Oops, let me go to the beginning slide. Okay, so you should be able to see my screen, right?
Yep.
Excellent. So my co-authors, I want to acknowledge co-authors, Dr. Manal Askar and Dr. Wayne Skaggs. The title is Design Drainage Rate to Optimize Crop Production. So as we know, we all agree that agricultural drainage is vital for crop production, but there are unintended consequences. This is a photo I took before the pandemic, August 2019. Every year, they would invite me to go there on a boat. It was an excellent experience, but we didn't do it this time around. So this is a photo from 2019. I found a clear plastic cup in the trash on the boat. So I scooped the water and I got a photo of this, and I was very excited to see this from close. You can see that the algae is floating in the water. That's so interesting. So basically, this is the water quality unintended consequence that one of the things that I'm trying to do here. So when you're designing a drainage system, drain spacing is one of the most important parameters. So that's so important for the drainage system. Why? Because it affects water quality, it affects the crop, and then it affects the cost too, because if you have narrower spacing, then you're gonna have to pay more, and the other way around too. This is another photo with a drone from the drainage water recycling site that we have in Michigan. So now that we know drain spacing is so important, how do we get drain spacing? The first option is that a drainage contractor or the designer goes based on judgment and experience. For example, drainage contractor that I talk with, they say, okay, in this region, I'm going to do 40 feet. So based on their judgment and experience, they pick a number. Or you could go to tables in local drainage guide. If your state has one, I know Minnesota has one, Iowa has one, but we don't have one in Michigan. So if you go to that local drainage guide, you'll see based on your soil and your drainage coefficient, you're going to get a range. For example, I'm going to give you an example. It says, go for a drain spacing of 30 to 60 feet. But which one do you go with? Do you go with the 30 or you go with the 60 or go somewhere in between? Well, how do you know? And eventually at the very end, I or someone else may tell the farmer, you need 35 feet, but they may look at their loan and they may not be able to afford it. They say, okay, I can't do it. I'm going to do 40 feet. So those are some of the deciding. That's how typically it's chosen and picked. But what is the best way to do this? The best way to come up with the drain spacing is you model the performance of alternative designs. By that, I mean that you model, let's say you got a specific field, you model 30 feet, right? Then you look at your economic outputs, crop yield, then you do 31 feet, 33, 34, 35, and you keep going until 60 feet or whatever you like. Then you look at all the data, you see which one of those spacings provided you with the best economical outcome with the shortest payback period over the long term. That's the best way. And just a side note, Chris mentioned we got a CIG. So we're using the same approach. We want to model performance of alternative saturated buffers for the other one and come up with the best design. So this idea of modeling the performance of alternatives is not just for drainage, not just for saturated buffers, it's for all of the conservation practices. Basically any engineering that you're doing, if you can model all of those and look for the best one, that's going to work best for you economically and also for other outcomes, water quality, crop yield. So once we do that, then we find this optimum drain spacing that will maximize profit. That's very important because by maximizing profit, in other words, that's going to be increasing the maximizing average annual return, and then the payback period is going to go down. So that's key. So why is this important? Why do we care about this optimal drain spacing? I touched a little bit at the beginning. I'm going to get into more detail. So if you pick something that is too wide, pick one of those spacings, then water removal is going to be slower than needed. And overall, water is going to be removed, less water is going to be removed in that scenario. And we don't really want that, right? We don't want too wide of a drain spacing because it's going to, in some years, it's going to result in yield loss due to wet stress because that water is not, you're not getting rid of that water quick enough. If you pick something that's too narrow than what you need, that's going to mean that water removal is going to be too quick. Overall, more water is going to be removed. And that's, again, we don't want that either, because that may result in yield loss due to drought stress. Imagine in June, July, it rains a little bit, and then you need to hold that water. I'm talking about conservation drainage. I know controlled drainage can hold water, but under conventional drainage, that water is going to be removed so quick that that may cause some drought stress. And so it also increases the cost of the drainage system. It's going to increase nutrient loss, and it's going to increase peak flow. We don't want that either. But if we have that optimum drain spacing based on that modeling performance, then we have that necessary water removal. And this is what we want. Why? Because that's going to give us optimum yield and it's going to maximize profit. That's the economics of the system. It's going to give us shortest payback period. That's what farmers are interested in. And also that's going to help with the water quality. Why? It's going to have water quality because it's going to help avoid the two narrow spacings, the one on the right side, because we are in the optimum spacing here. So let's see. So the objective was to help with this. We built on the idea of Dr. Wayne Skaggs that he did about 20 years ago. So we developed this empirical equation to predict the design drainage rate. This design drainage rate is the depth of water to be removed from the soil profile in 24 hours. So this is also known as the drainage coefficient that we commonly use when we talk to farmers or the practitioners. So it's the same thing. Drainage coefficient, we use that just for the accuracy of the terminology. I'm still using the drainage, the design drainage rate. It's the same thing. You design that, you put that in tools. And why is this important? Because if you use that design drainage rate, you put it in these tools, like the South Dakota drain spacing tool, that has the Huchat equation built in. Then the Huchat equation is going to give you that optimum drain spacing. That's going to maximize profit. That's key. So let's see what we did. So we went and we did drain mods simulations. My colleague, Dr. Manal Askar, with the help of Dr. Wayne Skaggs. These are 7 locations. We had 3 drain depths. We had 3 effective radii. We had 5 soils, so we could have different variations of soils. And there are weather data ranged from 1990 to 2019. That's a 30-year period, so we could have a long term. And these 7 locations are representing different climates. So we did different combinations of simulations of these. Let me show you one of the one. And in honor of the Drainage Research Forum, I'm showing the Waseca in Minnesota. So this is 1990 to 2019. I'm working on here, I'm showing you the 75 centimeter drain depth. That's 2.5 feet. Drummer City clay loam in Waseca. So let's look at one of those combinations. So I got relative yield in percent. I have drain spacing from 0 to 330 feet. That's a large number. And then here I've got average annual return. That's my profit, dollar per acre. So the higher the value of average annual return, the better. So let's look at yield for this. So as you can see, this is no surprise. There's no surprise here. Yield starts off well, and then as you keep going, increasing that spacing wider and wider, eventually it's as if there's an undrained field, I want to say. So in this undrained scenario, you can see here yield is pretty low, but yield starts off really well. Let's look at the profit. That's the interesting part. See how profit started off high and then it went down? Well, here is not very economical because the spacing is so narrow, even though yield is good, but it's just not economical. It's too narrow. But when you get to the peak, this is the optimum drain spacing. And in this scenario, it's 43 feet. So this is the idea behind those alternative designs, and all of those combinations of the location, soils, and drain depths. We developed all of the database, and then we calculated this optimum spacing for all of those combinations. Then we conducted a multiple linear regression, and in that regression, our outcome was a design drainage rate. That's again like the drainage coefficient. But this time, our predictors are the important parts. The predictors were the growing season, rainfall. This is very important, growing season, rainfall. You need to have your drain depth that you want to use in your design. I'm calling it the design drainage rate, the design drainage depth. Let's say you pick 2.5 or 3 or 4 feet. That's a predictor. Third, we have the equivalent saturated hydraulic conductivity. That's also a soil property, and it's very important. That's a third predictor. And the last one is the depth restrictive layer. Again, that's another one of those soil properties. So if you have these, you can use this empirical equation. This equation is for the Northeast region, the region that I was showing in green on the map, which includes the Midwest. That was like the basic idea behind it. We wanted to do most of the drainages, and it's going in, but we have another equation for other locations as well. This is for the Midwest, and you can see we've got a really good R squared. So basically the R squared means that the P, precipitation, depth, drain depth, K and D, these 4 explain 42% of the variation in the data. That's what it means. So that's pretty good, 82%. So we're very excited about this. So if you're, let's say you're in a I'll explain that one later then. So I'm going to get into some of the data. This I haven't shown before. So effective location on the design drainage rate. So what do I mean by that? So I've got my 7 locations here: Baton Rouge, Plymouth, Memphis, Waseca, Urbana, Albany, Lansing. And then I got design drainage rate in inches per day. And I've got growing season precipitation in inches on this side. So first I'm going to show you what these design drainage rates look like. Again, think about it of the drainage coefficient. So now basically you see Baton Rouge is the highest, Lansing is the lowest. Now I'm going to show you the precipitation trend during the growing season. So this is basically in order from the highest growing season precipitation to the lowest. So generally we see a trend of location. This one had 62 inches, if I'm right. No, it's not 62 inches. This is about 25 inches during the growing season, and Lansing had about, say, 19 approximately. So you can see the differences between these two. My point here with this slide is that location is vital and very important when you're designing a drainage system. So if you're designing a drainage system for, say, like somewhere Northwest Ohio, you want to take into account that weather in that location versus you're working someplace in Northwest Minnesota. So location is very important. You can see there is this relationship with general relationship as this precipitation goes down, and that's kind of intuitive. It makes sense. If you get less rainfall, then you need wider and wider spacing. So this design drainage rate, the drainage coefficient, has an inverse relationship with drain spacing. So if this one's the higher design drainage rate, it means that it's going to need a narrower. It rains a lot in Baton Rouge, and then the one in Lansing it rains less, so it can get away with the wider spacing. So I explained the empirical equation. This is the empirical equation, and these are the predictors. So anybody can go and use these and find this localized and site-specific design drainage rate. And then you can use it in any kind of tool that there is available, like the South Dakota tool that I mentioned. Then you can get an optimum spacing. So this is available to everybody. So if you look at some of these, like the design drain depth, that's pretty simple. It's your choice. You decide. Of course, there are other, I'm doing also some other research to show what it means if you go from shallow to deeper. That's coming in the future, but you can pick, let's say you pick 3 or 4. That's known. These two, the third and 4 of the K and the D, these are the soil properties. You can go to Web Soil Survey and you can get those properties for your local farm. The first one is a little bit harder because it's a weather long-term growing season rainfall for your location. It's not just from like 10 miles away with the airport, it's for that location. So to help with this, my colleague, Dr. Nejat Hashemi, and his decision support tool developers, they helped make a tool to actually use that equation. So if you go to the drainage website in Michigan, drainage design tools, and then the first one, click on that. Then you'll be taken to the tool. Just a heads up, this is the beta version. We're still working on the final version. So this is the pop-up message, click OK, and then you can zoom into any location within that red boundary. So I'm going to just zoom into South MSU campus where we got research farms. And then I'm going to click on the shape. I'm going to just draw a shape around. And then I'm going to change the corn planting date to 5th of May. I'm going to keep that design drainage rate as is. Then I'm going to hit calculate. So while this is going to start working and it's going to automatically get those weather, the third and fourth, the K, the saturated conductivity, and the depth to restrictive layer is going to automatically get those, and it's going to get the precipitation automatically as well. All I did is I gave it that design drainage rate and the target corn planting date. So the model now it's working in the background. So you see there's a layer at the bottom, the USA Soil Survey. If you click on that, you'll see the soil layer. So for this scenario, we have the optimum drain spacing of 59 feet. So basically, to conclude, the design drainage rate depends on many factors. I showed you the 4 predictors that were very important in our empirical equation. And the one that I want to highlight is that location. Location is very important because location affects that climate in that location. You need to know if you have what kind of temperature and what kind of rainfall you have, especially the rainfall that we're using here. So design drainage rate depends on many factors, including the precipitation. And we developed this empirical equation. You're welcome to use it outside of the tool. The tool will facilitate and make it easy to use that equation. And basically, one of the benefits is that there is a water quality benefit here. And that is that we will help avoid those too narrow of drain spacings. And with that, I thank you everybody for watching this presentation. And I want to thank Transforming Drainage for funding part of this research. Thank you.
All right, great. Thanks, Hassan. And again, in the interest of time, we'll hold questions until we get to the Q&A section right before lunch. So I'll go ahead and introduce our next speaker. Our next speaker is Sam Phillips, and Sam is a grad student at Iowa State University, and Sam's working with Matt Helmers and myself to monitor a couple of drainage water recycling sites in Iowa. These are a couple sites that were put in by a farmer that had some money when corn was $7 and wanted to play around with this idea, and so it's been a nice opportunity to monitor this practice while we wait for some other research sites to come on board. And so with that, I'll turn it over to Sam.
All right, thanks for the intro, Chris. Yeah, like Chris said, I'm a master's student at Iowa State, working with Matt and Chris and Satirius Arcantoulis on this project. So most of you, I'm sure, are plenty aware that tile drainage is very common in the state of Iowa to deal with excessive soil moisture. However, what is rare in Iowa is irrigation systems to combat deficit moisture stress. And really, farmers in Iowa can see both those challenges in the same growing season. So what drainage water recycling does is creates a sort of a closed system by rerouting the subsurface drainage to a storage pond where that excess moisture, which usually comes early in the growing season, can be stored and then used to supply irrigation for later in the growing season. And this is a really exciting practice because not only may it reduce downstream nutrient loading, it also has the potential to increase row crop yields. That graphic in the bottom right corner has a center pivot irrigation system on it. It does not need to be a above ground pivot irrigation to be drainage water recycling, but that is what this study is. So this site is located just south of Story City, Iowa. You can see that field is one long field with diagonal roads that are managed identically. There is subsurface drainage, and the only difference between the treatment and the control section is that the treatment portion in the southern part of the field there had a center pivot irrigation system installed in 2015. And that's supplied by that storage pond you see in the bottom right part of that graphic. So with that, this field has been planted to corn almost the entire last decade, with 2013 and 2020 being planted to soybeans. And both portions of the field have a pretty similar soil type makeup. A huge part of the monitoring has been the soil moisture tension sensors. I installed 6 sets, and at each set there is a sensor at 30, 60, and 90 centimeters below the soil surface, so we can get a look at what happens to soil moisture availability throughout the profile during these rainfall and irrigation events, and how that differs between the two areas. There was also rainfall and ET gauges installed on site for local weather data, an irrigation flow meter, so we can get a look at what's going on there. And a huge part of this project has been the historical Agfinity data, which details the agronomic management practices. and goes into great detail and allows me to spatially map that data and sort it into the treatment and the control zones of the field. And then this past summer, routine sampling of the storage pond water was done and will be analyzed for nutrient content. So I really like this graph here. You can see the large daily rainfall events that occur earlier in the growing season, and those sort of taper off as exampled by the 2019 data later in the year, which is when the crop water demand sort of skyrockets. And so that creates a large gap between the supply and the demand for water in the field, which sort of illustrates that there could be a use to supplemental irrigation in central Iowa. Here is some of the historical yield data from the site. Like I said, the irrigation system was installed in 2015. However, since then, it's only been used of 3 of those 5 growing seasons here, 2016, 17, and 19. And that's where you see that gap between the treatment area's yield and the control area's yield, as that irrigation was used to combat the moisture stress due to a lack of rainfall during the growing season. So to get an idea of how drainage water recycling may affect yields in the long term for producers, I use the APSIM crop model, which uses biophysical calculations that are iterated on a daily time step to show what's going on in the field. And it lets the user select all sorts of different modules to represent the soil, environmental, crop, and management properties. And they're really customizable, so you can change like the date and of an operation happening, different soil types, different weather events, and stuff like that. So calibration, like with any model, is an extremely important part of this. I calibrated using the yield data from 2014 through 2019, and also was able to bring in all of that agronomic management data from the Agfinity software, put that into the APSIM model, and then also brought in weather data from the Iowa State Horticulture Farm, which is only about 3 miles from the site, and brought that also into the APSIM model. And from there, to calibrate the model, I adjusted different cultivar properties of the corn module within APSIM. And you can see from figures 8 and 9 here, whether you're looking at the absolute yield benefit or yield benefit as a proportion of the yield of the control, there's a pretty strong relationship between what happened out in the field and what the APSIM model predicted. I'll go to the next slide, and you can see I calibrated it for yield benefit because that's really what we want to look at with the drainage water recycling, how it's changing between the 2 areas. This is the APSIM output, where the blue dots are the measured yield of the treatment area, and the red dots are the measured yield of the control area. And then the blue lines and red lines would be the APSIM yield that was predicted for that year. And there's a difference between the absolute yield, but the gap between the control and treatment area is really what we looked at here. 2017 and 2018 were sort of the major tests of calibration, with 2017 having that huge yield benefit due to the drainage water recycling, whereas in 2018 there was actually no irrigation utilized. And the model picked that up and predicted that the control area would actually outperform the treatment area because no irrigation was used. So there were a couple different scenarios that I looked at within that within the APSIM model. One, I wanted to see how different annual irrigation allocation limits might affect yield benefit. So there was a 4-inch limit, a 6-inch limit, and an unlimited scenario. There were 2 weather scenarios, one for like a baseline present day climate, and then with a bit of a climate change adjustment for the future. And then there were 2 management scenarios, which would be your rain-fed field, such as the control, and then the drainage water recycling field, like the treatment area. So this model is set up for a 40-year time period. Weather data was pulled from the Iowa Environmental Mesonet starting on January 1st, 1980 to December 31st, 2019 to get accurate local weather data. It was a continuous corn rotation using that same cultivar from the calibration period, and that was a 110-day variety of corn. To determine the planting dates, I used the 50th percentile Iowa plant date from the NASS data, and then fertilization was 150 kilograms of nitrogen per hectare 2 weeks before planting, and then a 50 kilogram nitrogen per hectare side dressing on June 10th. On the right part of the screen there, that's a look into the climate change module for APSIM, and how I adjusted it was to sort of model what's projected to happen in the Midwest by increasing spring rainfall by 15% and decreasing summer rainfall by 15%. Irrigation scheduling between the three scenarios was a huge undertaking, trying to get into the head of how a producer would act under the different limits. So the first thing was, obviously, if you're not allowed to use as much water, you're going to shorten up your irrigation window, so you're not going to start as early in the growing season, and you're going to make your decisions based on a longer time period previous to the day that you're thinking of irrigating on. A couple conditions that were the same in all three scenarios were that no irrigation took place after August 31st, as well as if there was a say 25 millimeters of rainfall for the day after the day that is scheduled to be irrigated on, that irrigation cycle was canceled because farmers generally have a good eye on the forecast and would not use up the resources to irrigate if they were going to get a heavy rainfall event the next day. So here's a look at the irrigation amount delivered in each scenario. Each scenario did have at least 1 year, and most of them had multiple years where there was no irrigation needed. And you'll see that sort of following common logic, the 4-inch scenarios hit their limit pretty frequently. The 6-inch scenarios did hit their limit, but not as much. And then with that climate change adjustment, those years had a higher mean annual irrigation amount. And in this, on these box plots, the solid line is the median and the dashed line is the mean value. So how did it affect yield? You'll see that in the climate change scenario, there was a increase in the mean yield benefit. However, there was also a lot larger variation. So keep that in mind. And it also showed that between the 4-inch and the 6-inch allocation limit, there was a difference. However, the 6-inch and the unlimited scenarios, the results there lead you to believe that a 6-inch limit would not be hamstringing success measured in yield benefit. So here's just a look at the APSIM output of yield over the time that this model was run. This shows the green line being the drainage water recycling yields, and the blue line being the rain-fed yields. So in years like 1985, obviously there's a huge gap, and then in flood years such as 1993, there's not that benefit there from drainage water recycling. So the next logical question would be, do those yield benefits translate to an improvement for farmers' bottom lines that would potentially spur on adaptation of this practice? And so obviously there's large upfront costs, investing in a center pivot system and a pump, and then accounting for any repairs that may need to be made. So these were counted as fixed costs that were the same every year. And then there's operating costs that are going to be based on how often you use the irrigation equipment, power to get the water out to the field, and then labor to get the irrigation cycle up and running. Revenues for this study were all estimated to be value added by the drainage water recycling system. So from that yield benefit. And with that, I also considered that grain costs are likely to be a little bit higher in years where you see a larger yield benefit because the average field in the state does not have a drainage water recycling system. So to try to put a number on the corn price, this was a very tricky process, but if you look at the average yield for Iowa corn over time, it is steadily increasing. And if you take that trend and compare it to the state's average yield in a given year, you can plot that against the corn price for that year. And it really depends on what time period you look at to see what that means in terms of cents per bushel. But if you look since 1960, for every bushel per acre that the state average yield was below the trend predicted state average yield, there was a 2-cent increase in the price for a bushel of corn. However, if you shorten up that window and look at even more recent data, on the right here, you can see that that was actually a 6-cent increase. So that's going to make a huge difference in your profit equations. And so we decided to look at using both models since 1960 for a more conservative estimate, and then since 2000 using more recent, putting an emphasis on more recent data. And so with model A here being the model that used data since 1960, you see you see lower corn prices with smaller variation, and with model B, there really hints that there could be something to the profit here. So here's how the profit equation would look under each of those scenarios if you use corn price model A. In baseline climate projections, you are going to be taking a loss in the drainage water recycling system. However, in the modeled climate change projections, that turns into a profit from the system. And just a reminder that this is the more conservative corn price model. If you use the model with more recent data, however, you can see pretty hefty gains in terms of dollars per acre per year under both the baseline climate data and the projected climate change data due to drainage water recycling. So next steps for this project, obviously we would like to expand this to as many crops as possible, soybeans being one for sure, and also seeing how cover crops could affect this potentially. More work needs to be done to affect the effluent nutrient levels to see if there is a reduction in non-point source pollution, and that would help us put a dollar amount on treatment for X amount of nutrients, say, and could potentially help with, say, a cost share program. And looking into the future, we're really excited to be able to start rolling in more site years and get more data as 2 new sites are in the process of being built. So with that, I want to acknowledge our partnering farmers who've been a huge help with this, and also our the Iowa Nutrient Research Center for the funding for this project.
All right, thanks, Sam. Just about 11:30, so why don't we go ahead and shift to Chad, and then we'll pick up questions at the end. So again, our final speaker this session is Chad Poole, and Chad is at North Carolina State University, and several of us got to see some of the work going on at his family's farm when we were out for a meeting in North Carolina before we got to enjoy some seafood and some Eastern Carolina barbecue, which I was pleased to get to have again, since it's been a long time since I've been in that part of the country. But again, given that travel isn't a constraint, it was great to be able to invite Chad to talk with us today. And so I'll turn it over to you, Chad.
Hey, Chris, can you hear me?
I can hear you. Sounds good.
Can you see the presentation?
Yep, it's up.
All right, sounds good. I just want to say thank you for inviting me. And, you know, out here in North Carolina, it's afternoon, so good afternoon. Good morning to you guys. Today, I was asked to talk about the development of automated drainage water management in North Carolina. And to get started with that, I think it's only appropriate that I recognize the team that has worked on this project over the years. Wayne Skaggs, George Cheshire, Muhammad Yusuf, and Tim Appleboom have been a part of this since it was first started. And we currently have a graduate student, Izan Bagari, who is working on the real-time water table management system. These individuals have been a big part of getting this system up and running. And at the same time, I'd like to recognize some contributors to the development of controlled drainage as a BMP in North Carolina, and that would be Robert Evans and Dr. Wendell Gillum, both of which were very active in the 1980s and 90s on working on controlled drainage as one of the primary reasons it's been accepted as a BMP for cost share in North Carolina. So before I go any further with the presentation, I just want to give you guys a background of why this is important to the state of North Carolina and why we decided to go down this route. We've had increasing water quality issues since the late 1970s in our river basins, multiple algae blooms and multiple fish kills. Problems have occurred in the Tar-Pamlico River Basin, the Neuse, the Roanoke, the Chowan, the Cape Fear, and many of our freshwater lakes, such as Mattamuskeet. As a result of that, a lot of the river basins have adopted reduction mandate rules of 30% in nitrogen from baseline levels in the 1991 through the 1995 time period. Basically, we have one primary mechanism in which that we can meet these mandates in multiple counties, and that is controlled drainage. It's pretty much the only mechanism in some of our coastal low-lying counties that we can meet these mandates. So it's very important that we use controlled drainage to reduce these levels. With that being said, in the early 2000s to the mid 2000s, we began to notice a reduction in the use of these control structures among our growers. There was actually an informal survey completed by the Nutrient Loss Assessment Work Group in 2008 that randomly selected 20 producers in the Neuse River Basin and basically interviewed them in the survey and found that 13 of the 20 were not managing the water control structures at all, and 7 only had partial management. And for you guys that are not aware, when I'm talking about water control structures in North Carolina, we typically have open ditches and canals, and we use a flashboard water control structure similar to the one you see on the bottom right-hand corner here, where you essentially cut salt-treated boards, place them in the structure, and that changes the elevation of the water level to put the system into controlled drainage. Given the fact that this INLU committee had seen that management was not occurring like we wanted it to, we put in for a national CIG grant. I worked with Dr. Wayne Skaggs on that, and we were working on developing an online drainage advisory for site-specific recommendations. And I got to work with 20 producers across Eastern North Carolina in the development of that project. And overwhelmingly, between those producers and what was observed with this survey producers, the biggest issue with management of these structures among the growers and the managers was the removal of the boards. Well, typically what happens is these salt-treated boards, when they come in contact with water, will swell and they get stuck in the structure. And it takes the use of power tools, whether it be chainsaws or reciprocating saws, to get the boards out. And that presented a great management problem for the growers. Now, to give you an idea of how important it is to the state, when it was accepted as a BMP, there was a state cost share program that is basically overseen by the Department of Soil and Water Conservation in North Carolina to fund these structures on a contractual basis with growers. We also have the federal EQIP program. I'm talking here strictly about the North Carolina cost share program. Right now, and this data is a few years old, we have over 1,270 contracts. The number of structures planned total over 4,000, with a total state investment of almost $4.5 million. It affects over 130,000 agricultural hectares, and these are predicted reductions in outflow of nitrogen if these systems were properly managed. The yield increases that we have seen from some of our studies would allude to about 1 million kilogram nitrogen reduction. The drainage reduction from reductions in drainage volumes would be about 725,000 kilograms. Denitrification potential of approximately 467,000 kilograms for a total of about 2.2 million kilograms of nitrogen per year, just with the state-sponsored program, not including the federal program. So it's kind of pivotal in the state of North Carolina that we get the management of these structures from a reduction potential. Now, going further, I thought it was only appropriate that I give one of the individuals that was here from the start of the development of controlled drainage as a BMP a chance to talk about the historic perspective of the practice in North Carolina.
Researchers in the departments of biological and agricultural engineering and soil science at North Carolina State University have conducted research on drainage water management or controlled drainage for about 40 years. Our field studies in the 1970s showed for the first time that drainage water management could be used during the winter months to substantially reduce the losses of nitrogen and phosphorus from drained lands. Because of the continued widespread interest about drainage water quality and the importance of this issue, researchers have repeated our studies in many states here in this country and around the world. We're still learning, and there's much more work to do in terms of research. But as a result of our past work and the application of this work by the farmers of Eastern North Carolina, we know quite a bit about the performance of this practice. For example, we know that properly managed controlled drainage conserves water and has been shown to increase corn and soybean yields by about 10%. The use of controlled drainage during the winter months can reduce nitrogen and phosphorus losses substantially. Nitrogen by 35 to 50% on average, and phosphorus by 25 to 35% on average. It varies some from soil to soil and year to year, but those are good average numbers. Drainage control structures are now being developed that can be automatically controlled from a remote location. The application of this new technology will make it possible for farmers to better manage drainage systems for water conservation, increased crop yields, and the reduction of the losses of contaminants in the drainage water to surface water. So we'll have a considerable positive environmental impact.
So with that, I want to talk about a little bit about the design objectives to dealing with this board issue that we were observing with these pilot studies. Another thing that came about the INLU committee survey was that particular committee was talking about reducing this 40% credit for controlled drainage down to 20 or less because of the lack of management, which is why we started this process of developing an automated based structure. Our design objectives were pretty simple: satisfy the production requirements of our growers, maximize their yields and profits, and minimize the environmental impacts of ag drainage in the landscape. To do that, the first thing we had to do was come up with a new design for the risers, and that would be the design of a manual gate structure that would be easy to use for our growers. It had to have key characteristics. It needed to be sealed with very little water leakage, easy to open and close. Ultimately, it needed to be retrofitted to all the existing systems. We have a huge number of them in North Carolina, and this system had to easily go into place. And we wanted the control elevation to be preset at 45 to 60 centimeters from the average field surface for water quality benefits. So I've got a video. This is a dated video because this process started almost 10 years ago, but hopefully you can make out what we came up with the manual system. We have a T-handle where the farmer can just come up, grab it, pull it up, and open it, releasing the water. That makes it cheaper, simpler to install, no electronics to fail. Just a very simple system to do similar things. It's just not an automated structure, or an automated system. To release the water, you simply pull the T-handle up, and the flow comes out, and if you want it to come out and shut it back off, it's just simply pushing it down. It's a much easier system than having to come out, remove the boards, and cut new boards and place them in the structure. So with phase one complete, and we had a viable gate option that could go in for replacement of the boards, it was time to move on to phase two. Phase two was to come up with an automated system that would manage these structures without the producer having to come out and do that. And we really, at first, didn't know how we were going to approach this, but we basically come up with a CPU controller, a solar panel, a self-contained battery unit. We set that weir elevation for the individual site at 45 to 60 centimeters, installed a trash safety grate for the gate valve that we put into the system, and started testing these in the field. But before we got there, we had to figure out how we were going to make those cost share compliant. And this is how we did it. This was the work that had been pioneered by Dr. Gillum, Dr. Skaggs, and Dr. Evans in North Carolina to develop management settings for controlled drainage when it was the typical wood and flashboard risers. This chart on the left-hand side of the screen is what's given out with all ag cost share contracts to the producers and managers in North Carolina. It's for each crop, there's a specific period and a recommended riser setting that goes in. These are only recommendations for the growers. If there's a tropical storm or a big event, they're allowed to make modifications to the system. But in general, these are what we recommend and what's given out with those cost share agreements. The time-based phase 2 system took advantage of this table in the programming. And this is how it looked in the controller unit. You basically you select your crop, and then there was a manual override for those situations when we had adverse weather conditions that the grower could come up and manually override the system. And this is what a typical scale model, this is what it would have looked like installed in one of the outlet ditches. So that system was field tested from 2014 and is still being currently tested now. And this is some preliminary data that I just put together. It's unpublished of the yield data for both corn and soybeans using the time-based system with a fixed weir height. And you can see from the data, corn's on top, that we really have not significantly reduced the yields. We haven't probably significantly increased them either, except maybe in 2018, but that's important because these structures were all managed electronically with no changes to the system during the entire growing season. So what we were able to do with this is to actually show that we could satisfy our production requirements with a time-based controlled drainage system and ultimately achieve the environmental benefits that we have been seeing with the standard controlled drainage system. So this is very, very important. Soybean yields are the same way, no differences in yields. So we're getting that environmental benefit of the structures and doing it automatically without the use of the grower having to go out and make these changes. Then we decided we needed a new phase. If we were going to carry this to the next level, we had to do more than just have a preset weir elevation. If we were going to see yield improvements, we needed to be able to make changes to the structure at any time during the growing season based on climatic conditions. And it was going to take more than just a drainage gate at the bottom to do that. And we come up with phase 3. This is a new adjustable top weir design. It's a 2-gate design that allows us to change the head in the ditch or the canal itself based on whatever climatic conditions we're seeing at the time. It also allows us to drain the system very similar to the time-based unit. And that allowed us to roll into phase 4. It's carrying these structures to the next level. Real-time automation with feedback from what's happening in the field. Eson, our graduate student, is currently doing his PhD work on this and has done a wonderful job. I'm looking forward to him to put his data out very shortly. And hopefully you guys will be able to see that and see how this system has functioned over the past few years. The key characteristics is programming for both drainage and sub-irrigation based on field water table feedback. He's currently using infield sensors for rainfall, the water table depth, and ditch levels in the field to make sure that we're conserving water in the ditch and not, anytime you have an automated system, if something goes wrong, you're not measuring the ditch levels, you could have flow over it that you don't want to have. So this is one of the reasons we have that sensor there, and it monitors that in a real-time situation. Now I want to go very briefly in the time I've got left and describe how the system functions. It's basically got 3 modes of actions: free drainage, controlled drainage, and sub-irrigation. It typically, if it's going to trigger free drainage, we have developed, or Eson has been working on developing field water table thresholds by crop, by the crop growth stage, where we see significant wet stresses if the water table goes above these levels. That's programmed into the system. If the water table were to go above on the right-hand side, this threshold, field water table 1, the computer controller would recognize that in real time and change the top gate first to drain the water level down and increase the drainage intensity. If that is not sufficient to lower that water table, that critical water table, it will open the bottom gate and increase the drainage intensity to the maximum that the system can allow. So that's one of the modes that occurs. The second mode is controlled drainage. And again, all these thresholds have been developed in DrainMod for the crops. We have 2 thresholds for controlled drainage. We know a range where the crops typically benefit from a yield standpoint by having the water table in this range. Those thresholds are programmed in by crop into the CPU. As long as the water table remains between these two thresholds, it will remain in controlled drainage. If the water table falls below the bottom threshold, field water table 3, then it goes into sub-irrigation mode. In sub-irrigation mode, all gates are closed and the top gate is raised to the highest level for sub-irrigation to maximize head to try and bring the water table back above this threshold. And that's essentially how the system works. And I've got a video in the field describing this process a little bit further where you guys can actually see the system in action. So we're at one of our drainage water management research projects. This is a collaborative project that I'm working on with Dr. Muhammad Yusuf and a graduate student, Isan Bagarelli. What we have here is an automated controlled drainage structure. We call it the smart generation of structures. This work this year is being sponsored by the Corn Growers Association of North Carolina, and it's previously been sponsored by the Soybean Growers Association. This system is functioning right now for corn crop, and it has the capabilities of basically looking at where the water table is in the field and making a decision of whether we need to drain excessive water or whether we would need to put water back into the system through sub-irrigation with its valve, based on where the crop is in its growth stage and the amount of water that's predicted to be used. There's some new changes to the system that's being tested. One, we have an LCD display where we can make sure that the crop setting is correct, that the plant date is correct. And then through this display, we can find out what's going on with the system as it's operating. You can go through this and see that currently right now, we are operating in sub-irrigation mode, that the water table is below our threshold for the stage the crop is in right now, and that we have two senders, two measurement devices out in the field, which you'll be able to see from the drone video, that's actually sending the water table information back to this processor through this antenna. For the corn, we have to have an antenna that gets us above the canopy so that communication signal can come through, and it's received here. Right now, we have two measurements. One is showing us from the first sender that the water table is 1.15 meters in the ground, about 36, 37 inches. And the other sender is showing us about 1.06 meters, which is about 34 or so inches off the top of my head. So we're trying to regulate that where it needs to be for the crop growth stage, and this system will do that, which is why it's telling us to be in sub-irrigation with the gates all the way up. Were we to get a big rain that put the water table at a critical threshold of being too high, the system would respond and drain that water out. So that's what's going on with this research data, and we're looking forward to being able to talk about the yield results coming up in the winter meetings. So with that, I just want to give you an idea of how the system functions. And this data will be published by Isan as he finishes up his work. But this is data from the 2019 soybean growing season at the site. This is the first year that the system was fully operational. And there's a couple of things I want to point out on the success of this system as we move forward. This is water table data from the ADI, which is the automated system, versus the free drainage system. Yeah, we can put the plant date into the system. This is when it occurred. And then sub-irrigation started occurring when the water table fell below our threshold. And as it continued, we were getting a drawdown in the water table. We realized that, and we decided that we were going to put a higher sub-irrigation head in. So we changed the code and put a higher head in. And as you can see, that made a difference in our ability to regulate the water table during the growing season. It still stayed below our threshold. We couldn't get it up because the ET from the plants were so high during this period until this rainfall event occurred. But it definitely made a huge impact and a significant impact compared to the free drainage system, as you can see. Some of the things with research, this system has over 5,000 lines of code. So it's very intense in how it goes through and checks all these parameters and what it's doing by crop and by growth stage. But you learn a lot. When we got going, when we actually processed this data, we were in sub-irrigation mode, and all of a sudden we saw a change in the water table elevation here. It went up drastically. Pretty much what happened here is the plant reached physiological maturity, and we were continuing to sub-irrigate. So we wasted water during this period with this system. That's one of the things we learned last year that we had to make adjustments for in the code, is actually to identify when this occurs so we don't waste water. You know, sub-irrigation should have stopped at this point. But that's why it's called research. That's what we're learning from it, and that's the improvements that we're continuously making with the system. And with that, I've got one slide left to sum up everything and where we're going with the next phase of real-time automation, some of the future plans that we have. And first and foremost, one of the things that we'd like to do is incorporate soil moisture sensing in the root zone. That's not necessarily that critical from the standpoint of a sub-irrigation approach, but what we'd like to do is take this system and make it a total ag water management system, where it not only controls the drainage outflow and subsurface irrigation controls, but we can tie it into surface irrigation systems. In order to do that, we need to keep track of the soil moisture in the root zone. That's coming in the future. That's something we're going to be looking into doing with the new generation coming forth. You heard Dr. Skaggs talk about remote access and controls. That is something that we'd like to see in the next generation of structures, that we can have access to it from cell phones or from the web, so we can remotely monitor it. We can upload codes or make changes if we need to remotely. And finally, one of the things that we're really thinking about doing is taking a machine learning approach to management. Yeah, these systems have the capabilities of looking at what's going on in real time. We can use them to take a machine learning approach to water table control and management, soil moisture management. Actually learning how the drainage system responds based on different drainage intensities, based on different climatic situations, and be able to do a better job of managing the system, draining what we need to, adding just enough water to get us back to where we need to be, instead of having repeated over management. And the machine learning approach would probably carry us in that direction. So that's something that we're planning to do in the future. And with that, I'd just like to acknowledge the groups that have funded the research and helped us along the way, and turn it back over to you, Chris.
All right, great, fantastic. Thanks, Chad. It's great to see the progress of that system. So some questions have come in. First question from Jane for you, Chad, was if those videos are online.
Yeah, James, some of those videos are online. They're in a little bit different format. The Blacklands Farm Managers Association, through our extension group, has several of those videos. The one with Wayne and the one with the manual structure is not online, but you guys will have it as part of this presentation.
All right. Then next question was, what's the cost of the system and how much area can it manage?
That is a compounded question. Honestly, we haven't even sat down and put a number on the cost of this, and it's really because we're doing research on it. The sensors that we're using are fairly expensive. We've tried to go through the process of working on the control unit, getting the cost down for that, but that's really not been our goal here. Our goal is to come up with a system that works, that's feasible, that we can stand behind, and then it's somebody else's job to figure out how to make it cost effective. That's the way we've approached it.
All right. And then what's the water source for sub-irrigation, and is that readily available and cost effective for that region?
Okay, that particular site that I showed the video on, we actually have a deep well. It's in our Castle Hane aquifer. It's a fairly good water source there. So we actually have a continuous supply of water for sub-irrigation for that site. We are using this technology on a water capture and reuse site that we have. And that is strictly surface runoff water that's caught in a holding pond. So it's adaptable. I mean, it's just like any other system. As long as you've got water available, you can run it through the automatic control.
All right. How if we go ahead and shift up to some questions for Laura. And first one there from Tyler. Has anyone looked at measuring denitrification with tannins in the DOC substrate for the process? It would be interesting to see if what we are trying to prevent is actually assisting in the denitrification process.
Short answer to your question, Tyler, no, we haven't looked at that. We were actually more concerned that the very high levels of tannic acid would inhibit the denitrifiers rather than provide a benefit. But I actually was having a nice chat online with, sorry, that was my cat's tail. Nice chat with Chad Penn while this is going on. And he mentioned that maybe it could be possible that there are some inhibitory effects of some of the phenols in the oak leachate that were inhibiting some of the other things going on. And so the denitrifiers could do even more of their job. I think there's a lot going on with the water chemistry that we just really don't understand. But yeah, the oak was just a surprising thing for us.
Next one from Shane. Any reason why the ash wood had a low N2O potential compared to the oak and mixed hardwood?
No, we were very surprised by that. And the student who did the DEA test had done a number of DEA tests before, and she triple checked everything. We just couldn't figure out what was going on with the no nitrous oxide from the ash. No answer there, but that was an interesting finding for sure.
Okay. And then from Dennis, what size wood chips perform best, even if the standard says 1 to 2 inches? Have experiments been conducted that looked at size effects on nitrate removal?
There have been some really good studies with comparing different particle size of different wood chips. The studies in general find that there's no impact of particle size on nitrate removal rate. So small wood chips give the same nitrate removal rate as big wood chips. I feel like there's more to that than we're really seeing, because of course particle size and surface area is such an important factor for a lot of biological processes, as well as chemical absorption processes like Chad talked about. I think the NRCS standard recommends coarse because of the flow properties rather than surface area effects. But there's been some good studies on that, but again, I think there's more to that too.
Okay. And then from Mark, were wood chips derived from a chipper that debarked in logs? Was there an estimate of heartwood ratio to total chips?
No, and our little residential chipper that we have at my house that we used did not debark the branches that we used for that specific study. But I think, as you know, Mark, bark and heartwood are very, very different in terms of chemical composition. But for this particular study, we were using relatively smaller branches that did contain some bark.
All right. And a question for Hassan. I was wondering if you considered initial soil moisture effects, non-growing season precipitation on drainage rate.
Yes, we did consider those because the background model that we simulated was drain mod. So we did consider those, and basically everything that you have in drain mod, you got your soil water conditions, what the crop effective root depth is, and so on. I could go on. Soil parameters, weather, heat index, and so on. We did. Good
Okay.
question.
All right.
Thank you.
Then last question here for Sam from Alec. As part of next steps, are you going to look at subsurface irrigation as opposed to sprinkler? And you can take a stab at it, and I can weigh in on that one as well, if that helps Sam.
Yeah, I talked to Alex in the comments, but the next 2 sites are going to be sprinkler irrigation, and there is a sub-irrigation system that the same farmer of the site that I use has. We just haven't seen the same yield effect. So I'll let you take over from there, Chris.
All right. Yeah, and I'll just add that there's potential for a new site that would use subsurface drip as the irrigation system. The 2 new ones coming on just didn't lend themselves to sub-irrigation. This third potential one, the producer's already wanting to put in a subsurface drip system, so that would be another nice comparison to look at that as an irrigation option. And a couple more questions to come in. One for Chad. You said that controlled drainage is your only option in North Carolina for reducing nitrate losses. What about wetlands, saturated buffers, bioreactors, et cetera? Are these not usable in that context?
Let me clarify that. I said it was the only viable option in a couple counties. We have multiple other BMPs that are used across North Carolina to meet those nutrient mandates, particularly no-till and nutrient management. But we have 2 counties in the coastal, down right close to the ocean, that their only BMP is controlled drainage. And should that reduction have fallen from 40% to less than 20, they would not have made the mandate, simply because that farm, that's the only BMP they had on it. It encompasses almost 40,000 acres, and it's one producer. So just let me be clear about that. It's not the only tool. It's just the only tool in 1 or 2 counties in the state.
Okay. Okay, great. Then one last question here for Hassan. Do you plan to look at potential adjustments to the optimum drainage rates to incorporate water quality objectives?
Great question, Gary. I've been thinking about, over the years, I've been wondering where there's the local drainage guide, where the drainage coefficient is, and the sum of those ranges. That's something that can be done with this modeling approach to actually fine tune some of those, because there's such a big range that it makes a recommendation for a big range, but that can be updated with this kind of approach, with the modeling approach and alternative designs. And even our current data set can actually be used to fine tune and get closer to those recommendations. So there is potential. I don't know the pathway to do that, but there is potential to update these NRCS tables and local drainage guides.
All right, great. Well, we've hit the lunch hour, and so thanks again to our speakers, Laura, Hassan, Sam, and Chad. Another great set of talks.